Hi, class. Welcome to our discussion on some geometric transformations. So, we are done with discussing the basics of linear transformations, and now let's go through affine transformation. So, again, affine transformation is a combination of a linear transformation and a fixed vector. All linear transformations are also affine transformations. So we have two types, we have translation and glide reflection. So these are like almost linear transformations in a sense that they preserve key characteristics of a vector space. We say that they are almost linear transformations because they possess most of the same properties as of linear transformation. And then for its formal definition, a fine transformation can be formally defined as a function between two vector spaces uh, that forms f of x is equal to L of x plus y for some linear transformation L and some fixed vector y. So, for example, as when we have vector b, let's have b is equal to 1/2, and then we are adding it to vector a, which is 5 negative 1. So if we add that, the addition property of linear transformations, just like what we discussed earlier, is still preserved here in affine transformation. Okay, so it's still gonna be equal to the sum of each component. So that's 6, 1. Okay. So we are simply adding the x coordinates and the y coordinates of the two vectors respectively. So it can be interpreted as shifting the point, right? Shifting the point from point A 1 unit to uh, maybe 1 unit to the right and 2 units upward, for example, right? So we are just shifting it from where we originally have it. Okay. So wait a sec. Okay. So our original vector is A, right? And then we are adding the fixed vector B. Okay. So this is like the Y in the definition. So originally we have 5, negative 1. So now that's going to be shifted. Let me get a Cartesian plane to show it. Okay. So again, this is our original point A, 5, negative 1. And then since we are adding a vector, fixed vector 1, 2, so that just means we move 1 unit to the right, right? 1 unit to the right and 1 unit up. 2 units up because it's 1, 2. So this is the location of our new point. So if that property is also applicable to a transformation, then we can call it affine transformation. So that's why all linear transformations are affine transformations because this property are also is also required for something to be called a linear transformation. Okay, so let's have some examples. So again, just to reiterate, all linear transformations are affine transformations. And then the other interpretation or the reverse is not the same. Not all affine transformations are linear because in linear transformations we always map it to the origin itself. But that's not the case because if we have the origin and we move it 1 unit to the right, then it's not going to be at the origin anymore, right? So not all linear transformations are affine. Not all affine transformations are linear transformations. Now, let's go through some examples. The first example that we have, and you've most probably have done already, is translation. So when we had our discussion on Cartesian plane, we've already done this before. The movement to the left, to the right. So you've already done translation before. So translation is an affine transformation that shifts all points in an image by a fixed amount along the x and y axis. In standard form, this translation transformation by a fixed vector y can be written as t sub y of x plus I sub x, I of x plus y, where I is the identity that maps a vector to itself. So this is what it looks like, right? So the original image is there, and here the translated image shows us that we've moved up and to the right, right? So that's a translation. So examples that we have for translations in real life. So we have the patterns. So the design of woven fabrics or textile designs, as you can see here. So here, the diagonal stripes are copied along the horizontal line, right? So it's just repeat, a repetition here. So that's an example of translation. Now, let's have linear transformation plus translation. So this is what it's gonna look like. So for example, we have this original image. So we can move it up, translate up and to the right. After that, we can reflect it, right? Or reflect it first, because reflection requires preservation of the origin, right? So reflect it first and then move it up and then to the right. And then here, rotate it first and then translate it. And then we can also have dilation with translation. Okay. So those are the examples that we have. Next, glide trans glide reflection, sorry, or transflection. So this one is defined as an affine transformation of an image that is obtained by reflecting an image with respect to a line of symmetry and then translating it in a direction parallel to that line. So glide direction is done by flipping, then sliding an object. The order of performing the two transformations actually does not matter, as both orders will produce the same result. So we can flip, then slide, or vice versa. So one of the most famous examples of glide transformation are footprints, right? So we slide it and then we flip it to get the next image. So it is a composition of two affine transformations. In higher math courses, you will prove that indeed the composition of two affine transformation is also an affine transformation. So just a reminder, the discussion that we are having with regards to linear transformations and affine transformations are the very foundational discussion. So we only have two components here. But when you search for it, we mostly have usually have four or six components for discussions like this. But for now, we are just keeping it in mind how it works. Okay. So as you can see here, yeah, we have this example for transformation, a fine transformation. So you can also use that um, in applications. Okay, so that concludes our discussion of affine transformation and geometric transformation in general. Again, if you have any questions or clarifications, just don't hesitate to message me, send me a DM, or put a comment in uh, the the post. Okay, have a great day.